Chapter 4, Chemical Bonding. Lewis structure. At the end of this lesson, hopefully, you can write the Lewis symbol for an atom. Valence electron play an important role in drawing the Lewis symbol. So what is valence electron? So valence electron are the outer shell electron of an atom. Valence electron also the electron that participate in chemical bonding. We can determine the number of valence electron from the group. So we have group 1, group 2, 13 until 17. So for group 1, the number of valence electron is 1. For group 2, the number of valence electron is 2. So the number of valence electron for group 1 and group 2 is the same. Okay, how about group 13? The number of valence electron for group 13 is 3. For group 14, 4, group 15, 16 and 17. So what is Lewis symbol? It consists of the symbol of an element, one dot or one cross for each valence electron in an atom of the element. Elements in the same group have similar outer electron configuration. For example, lithium and sodium, both are in the same group. Both have the same valence electron, and the valence electron are represented by using dot or cross. So this is element in the periodic table. So we have group 1, group 2. So group 1, there are 1 valence electron. For group 2, there are 2 valence electron. And we need to place the valence electron as far apart as possible. So the 2 electrons should be put in opposite side. Okay, let's see beryllium. The first electron was put at the left side and another one is put at the right side. Okay, let's see for group 14. So group 14, there are 4 valence electrons. So the 4 valence electrons are placed at the top, at the bottom, at the right side and the left side. The electron was put as far apart as possible. Okay, let's see example for group 16. So there are 6 valence electrons. So the electron, firstly we put at the left side, then right side, then at the top, at the bottom, then at the top again, and then at the bottom. So this is the Lewis symbol for element. Next, our objective is to state the octet rule and describe how atoms obtain the octet configuration. Octet rules. Atom combine until it is surrounded by 8 valence electrons in order to achieve a more stable electronic configuration. Maximum stability results when an atom is isoelectronic with a noble gas. So noble gas configuration is Ns2 and P6. Orbital S full of electron, orbital P also full of electron. So this is stable. So atom can achieve noble gas configuration through transfer of electron and sharing of electron. The electron configuration of ion. Ion has stable electronic configuration of either the noble gas configuration, pseudo-noble gas configuration, half-filled orbital. Okay, let's see the first stability, that is noble gas configuration. Group 1, Group 2 and 13 element transfer valence electron to form cation with noble gas configuration. Example, sodium. Sodium have 11 electrons, so the electronic configuration for sodium is 1s2, 2s2, 2p6, 3s1. So to achieve stability of noble gas, sodium atom need to remove one electron from 3s to form 1s2, 2s2, 2p6. So this electronic configuration is the same with neon. So neon is noble gas. So noble gas is stable. Magnesium. Magnesium will remove 2 electrons from 3s to achieve stability of noble gas. So the electronic configuration for magnesium ion is 1s2, 2s2, 2p6. So this electronic configuration is isoelectronic with neon. Aluminium have the same electronic configuration, that is 1s2, 2s2, 2p6. Group 15, 16 and 17 accept electron to form an ion with noble gas configuration. Nitrogen. There are 7 electrons, so the electronic configuration is 1s2, 2s2, 2p3. To achieve stability, nitrogen atom need to accept 3 electrons, so it becomes N3 minus ion, and the electronic configuration for this ion is 1s2, 2s2, 2p6. So this electronic configuration is isoelectronic with neon, noble gas. Okay, for oxygen ion, it's also isoelectronic with neon. Okay, so what is electronic configuration for oxygen atom? Okay, the electronic configuration for oxygen atom is 1s2, 2s2, 2p, 2p4. So oxygen atom need to gain 2 electrons to achieve stability of noble gas. Okay, how about fluorine atom? What is the electronic configuration for fluorine? Yes, the electronic configuration for fluorine is 1s2, 2s2, 2p, 2p5. Pseudo-noble gas configuration. Pseudo means false. So pseudo-noble gas means that the atom has similar electron configuration with noble gas. The valence electron configuration needed is either Ns2, Np6, Nd10 or Ns2, Np6, Nd10, and F14. For d block element, electron from 4s orbital will be transferred first before the 3d orbital. D block element don't need electron to achieve pseudo-noble gas configuration. Example, zinc. So zinc need to remove 2 electrons from 4s to achieve pseudo-noble gas configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Pseudo-noble gas configuration. Half-filled orbital. D block element can also donate or receive electron to achieve half-filled orbital, which is stable. Example, manganese. The electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So, manganese will remove 2 electrons from 4s to achieve half-filled orbital. So, the valence electron configuration for Mn2 plus is 3s2, 3p6, 3d5. So, this is stability of half-filled orbital. Another example is Fe. So, Fe will remove 2 electrons from 4s and 1 electron from 3d to achieve half-filled orbital. Okay, next objective. Compare the bond length between single, double, and triple bond. What is bond length? So as we can see from this diagram, we have 2 atoms here. So the bond length is between the 2 nuclei. So bond length is the distance between nuclei of 2 covalently bonded atoms in a molecule. For a given pair of atoms, single bond, the bond length for the single bond is greater than double bond, and the double bond is greater than triple bond. Comparison of the bond length between single, double, and triple bond. Multiple bonds are shorter than single covalent bond. For a given pair of atoms such as carbon and nitrogen, triple bonds are shorter than double bond, which in turn are shorter than single bond. Okay, now let's see the relation of bond order, bond length, and bond energy. So we have here carbon bonding with oxygen, carbon bonding with carbon, nitrogen bonding with nitrogen. So let's see nitrogen. So the bond order we have here is single, double, triple. Okay, the bond length for the single bond is 146, for the double bond is 122, and for the triple bond is 110. So the triple bond is shortest compared to double, compared to single bond. Okay, let's see the bond energy. Bond energy for single bond is 160, for double bond is 480, and triple bond 945. So we can see that the relation between bond length and the bond energy is inversely proportional. The shortest the bond length, the greater the bond energy. So we conclude here, when the bond order increase, the bonds are shorter and stronger.